All right, so I'm excited to have yet another good friend coming to speak to you guys. This is a more recent friend new, as he is here in the UC system. So Mike Hyland is an assistant professor at the University of California at Irvine. He is in civil and environmental engineering there, so up some of your alleys. He's also an affiliate of the ITS there. So as many of you know, we have 4 of these ITSs that jointly do research together. And so Irvine is one of those. So many of the folks that you guys work with quite a bit know Mike pretty well already through our affiliated ITSs. He did his PhD from Northwestern University, also in civil and environmental engineering. And his research focuses on modeling and analysis techniques to support planning, design, management, and operations of multimodal transportation systems. And specifically, part of what you're going to hear about today, he focuses on emerging transportation innovations and their impacts, one of which is microtransit, which is part of what we're going to, or much of what we're going to hear about today. So with that, let's welcome Dr. Mike Hyland. Remember to sign in, you guys.
So first, thanks for having me. I'm very happy to spend the Friday with you. I hope you're happy to spend the Friday with me. It's great to be here at Davis. This is my second time. I still haven't got a great look at the campus, but maybe I'll do that at some point in my career. So as Gary said, today we'll be talking about mainly microtransit, titled Operation Design of Microtransit Systems. The talk will be mostly about operations, but I'm happy to answer any questions about the design of these services as well. I'll get into my bio myself in a few slides, but I have this kind of layout, this read planning, design, management, operations. I kind of think of those as varying in terms of the temporal time frame, planning being long-term decisions, design also being long-term but more specific, management and operations being more on the ground, shorter temporal resolutions. In the case of operations, what should we do 5 seconds? All right, so the talk I'll be giving today is really associated with 2 ongoing research studies. Just want to give some credit to some co-authors here. So my former master's student, Zifan Wang, the 2 current PhD students, Navjo and Young Hoon, and some colleagues at Argonne National Labs. Argonne, actually the organization that funded this research for the Department of Energy. And I have an ongoing research project with the UC ITS, part of the RIMI program, Resilient, Innovative, and Ability Initiative, with Susie Pike and Yanjing here, and my students, Ping-Kong Yang and Siwei OCI. All right, so this is the agenda for the rest of the talk today. We give a bit of a bio on myself. I have a lot of time, so we're going to talk about myself during that period. Talk a little about my research program. These will both just be one slide. We'll spend most of our time on this completed study here, which is about operating on-demand microtransit services. And then at the very end, I have one slide that talks about some of the important design considerations when designing microtransit services, microtransit systems. All right, so a little bit about me. I go by Mike. I would put Michael on all my formal things, but for the most part, everyone calls me Mike. 2 people call me Mikey, but I probably shouldn't. From Pittsburgh, Pennsylvania originally. My parents have been working from home since the 1980s, so they were kind of ahead of the trend there. My dad's office was always in our basement. My mom either worked with my dad or at the school that I went to. We drove most places. As a family, and particularly my dad, has an extreme dislike for traffic congestion. So I think that's probably what motivated me to get into transportation initially. I don't really do anything with traffic anymore, traffic congestion or traffic signals, even though that's kind of what got me into this field. So as Gary said, there's my background. I guess a couple of things to mention here. It was my intro to transportation engineering course where I was like, I don't want to do structures anymore. I want to do transportation. I want to solve challenges related to energy and transportation. At the time, high-speed rail was kind of the cool new technology that everyone was talking about. I was excited about it. Didn't go very far in many places. Unintended fun there. Did my master's at Cornell as well, and then my PhD at Northwestern. Some of my hobbies, I like to play and watch basketball. It used to be in that order. Now it's the reverse. I tend to watch more and play less, but still a big basketball fan. I think it's probably many of you, I like to hike, I like to travel, I like to camp. I'm doing that more with my family now than I used to 10 years ago. And then as of 2 weeks ago, I got a gardening plot in the Irvine community. Okay, so let's talk a little bit about my research program. what interests me, where am I spending my time, what I think are the important topics in the transportation sphere. Well, the important topics that I can contribute to is probably a better way to say it. So analysis and modeling is broadly what I do. I feel relatively comfortable modeling many parts of the passenger transportation system and some parts of the freight transportation system. You said in my bio earlier, I'm particularly interested in innovations or emerging technologies in the transportation space. These include things like transportation network companies, ride-hailing, shared ride services, microtransit. My dissertation was on driverless vehicle fleets of automated vehicles, kind of an Uber context without the drivers. Shared micromobility systems, e-bikes, e-scooters in the shared context. I've done some work on electric vehicle charging infrastructure for both passenger transportation and freight transportation systems. And then finally here, I've done some work on crowd shifting as well. So the methods I tend to use include optimization. I teach our optimization course at the undergraduate and graduate level at UC Irvine. Focus mainly on linear integer programming. I don't know much or do much with nonlinear programming. I've also been doing what's now called sequential decision analytics, kind of advancements over old school dynamic programming. Decisions that need to be made now, and then you're going to make a decision again in 5 minutes. That's what I'm going to be talking about mainly today, or in 30 seconds, or in 3 seconds, depending on the case. I'm also become quite interested in long-term regional planning, the models associated with long-term regional planning, the equity implications of long-term regional planning decisions, and really how we can incorporate mobility innovations into those plans and represent those mobility innovations in models that support the planning decisions. All right, so let's get into the focus of today's talk, which is about operating on-demand microtransit systems with virtual stops. So some acronyms first. I'll be using MOD or mobility on demand. I'll tend to just say the whole word, but just in case you see it on the slide, I don't read it. Here's the acronyms. C to C being corner to corner, and that's opposed to D to D being door to door, whether or not the vehicle is coming exactly to your trip origin, or you might have to walk a little bit. RV being request vehicle matching, PUDO being pickup and or drop off. So these are a useful acronym when describing a Uber and Lyft type service. Ride pooling being RP and RH being ride hailing, and then you might have heard of VMT or VKT. I'll be mostly using vehicle kilometers traveled here today. All right, so a little bit more about what we'll be talking about. What I mean by mobility on demand is effectively where you, the user, go on your phone application, make a request, and want the vehicle to come immediately. This is opposed to a schedule-based service where you can still go on your app or your web browser, schedule a ride sometime in the future. So mainly be talking about on-demand or immediate requests. Shared ride, that is, you might be inside of a vehicle with strangers who you didn't know before you got into the vehicle. Virtual stops, this is the idea I kind of mentioned with the corner to corner versus door to door. So rather than just using physical infrastructure-based stops like a bus stop, and then the other end of the possible spectrum being the vehicles come pick you up wherever you want. Somewhere in the middle is this idea of virtual stops, right? So bus stops might be a good example if the local regulations allow you to use bus stops, but you might also use other places of interest or places that are convenient for vehicles to pull over to pick up passengers. So yeah, I'll be using C to C or corner to corner also to refer to virtual stops. So I think it's useful to make kind of a compare and contrast between the public sector version of microtransit and the private sector version of microtransit. I'll try to do that throughout the talk today. Usually the term microtransit, or always the term microtransit, is used in the public transport version, whereas things like shared ride services, ride sharing services is a terminology used for a private sector based service. Okay, I think this is the way I oftentimes like to think about where the emerging technologies, smartphones, GPS, allow us to make improvements in the transportation system. And if we think historically, it used to mainly just be private vehicles, which you own yourselves, or taxis on the one end, which are only available in a select number of cities in the US, and public transit on the other end of the spectrum. These spectrums being person throughput capacity of the system, or fixed route, fixed schedule to move a lot of people in a few number of vehicles quite efficiently. But depending on where you live, the quality of service associated with fixed route service might not be high. In some cases, you might live along the fixed route trunk and work and have a lot of activities along that line as well. Once you do get high quality of service, but that's no guarantee. Whereas with taxis, you're getting picked up where you want to get picked up at, and you're getting dropped off where you want to get dropped off. So between these two ends of the spectrum, we have a large number of modes that have started to exist and could potentially exist. I think primarily based on technologies, particularly the smartphone and GPS. So these include things like ride sharing, van pooling, historically demand responsive, flexible transit systems, or what I'm going to be referring to today as microtransit systems. With the idea that ideally we can find some of these services that under some context outperform every other service along both of these dimensions. More realistic is that there's always going to be trade-offs. You're going to be trading off quality of service versus the capacity or the efficiency of the system. Okay, so I have a couple slides here laying out some of the differences between existing modes and a microtransit-based service. So we have on this slide here 3 different travelers, O and D being the traveler's origins and destinations. And in this case, 2 different modes that can serve this set of 3 traveler requests. In the taxi case, you can see we have a lot more yellow lines, which means a lot more vehicle miles traveled, which is negative, of course, but people don't have to walk at all. Whereas with the blue lines, people have to walk to the bus stops, to and from the bus stops, more efficient in terms of vehicle miles traveled, but the quality of service might not be that high. This slide here, we have somewhere in the middle, flexible microtransit-based services, where people still have to walk a little bit, vehicle miles traveled are a little bit larger than a fixed route public transit service. You're kind of meeting in the middle in terms of reducing walk times and reducing vehicle fees. And then here's the 4 different service options that I'm going to be comparing throughout the rest of my talk today. Well, I shouldn't say that, actually. We're not going to be comparing fixed route transit. We're going to be comparing walking enabled corner to corner shared ride services, door to door shared ride services, door to door ride hailing, and corner to corner ride hailing, which actually, as a result, will show have some benefits on their own. So that is, we're not trying to pack strangers into a vehicle, but we're still having people walk a block or 2 to get access to their UberX or taxi service. Could incorporate corner to corner. All right, so the objectives of this study are as follows: to develop a decision modeling framework, algorithmic strategies, and operational policies in order to make this corner-to-corner shared ride microtransit service actually work well. We want to do that at scale. That is a large number of vehicles, a large number of requests, not just 3 or 4 vehicles that you might see in some of the studies in the literature. We want the algorithms and the decision models to work in realistic settings, right? In the real world, the network can become congested. The vehicles themselves can actually congest the network. We're going to use simulation models that actually capture those realistic components of a real world transportation network. And then again, speaking back to my prior Pareto frontier in terms of quality of service and capacity throughput of the system, we would like to identify conditions under which the microtransit service works quite well. We want to do all that algorithmic work, all that optimization, simulation modeling in order to identify the trade-offs between corner-to-corner service, door-to-door service, and walking-enabled service and non-walking enabled services. So these are the 4 services I'll be talking about today. All right, so what are the challenges that I and my research team face going into this? The first is the size of the decision problem. So as I mentioned, you can imagine, right? Every few minutes or every few seconds, I'm a central operator, I have to match my vehicles to people who've made requests on their smartphones, right? That's kind of the standard for Uber and Lyft. If there's strangers that are in the vehicle as well, which means I might have to deviate from my origin to destination to pick up other travelers, that makes the problem more complicated. But what makes it even more complicated is you, when you make your request, don't have a fixed pickup and drop off location. I, the central operator, also have to tell you where to walk to and where to walk from, which for even a few vehicles and a half dozen requests, actually becomes computationally intractable using exact solution methods. So we have to use heuristics to solve this problem. Beyond that, because we are going to be dealing with a large number of vehicles and a large number of requests, and we're going to be using realistic network models, we would like to be able to know how long it would take for every vehicle to get to every possible request in the network. To do that, we need to solve a shortest path problem, which is in and of itself not a particularly challenging problem to solve. But if we need to solve tens of thousands of these every 5 seconds, it becomes a bit of an issue, because the vehicles themselves are moving and the requests are popping up in locations. And then the third challenge is that there is uncertainty or stochasticity everywhere inside of a real-world transportation system. And one of the potential negative outcomes of this stochasticity is that you have vehicles waiting at pickup locations for travelers to walk there, which can be highly inconvenient for the people that are inside the vehicle and highly inefficient from a fleet operations perspective to not be utilizing your vehicle, actually moving people towards their destinations. There's also challenges around the dynamics of the problem. So requests are popping up all the time. The state of the system is changing. Ingestion is changing as the day moves forward in time. Okay, so a little bit more about some of these challenges. One here is because it is a dynamic system, because you don't know where all of your future requests are going to be, it's often the case, or always the case, that a vehicle has a last planned drop-off. Okay, I have a set of requests I have to serve. I'm going to pick them up and I'm going to drop them off. What do I do when it comes to determining where the drop-off location should be for the last request? Well, I can take that request directly to their final destination. High quality of service, but might be inefficient for the requests that might pop up in the future that I don't know about now. Or I can just stay on the main line here in the third option, which means that person's going to have to walk a long distance. So you have to come up with some policies for how to handle this. I already mentioned the challenge associated with vehicles waiting for travelers at pickup locations. You can obviously mitigate this issue by having the vehicle drive closer to the traveler's original pickup location, as opposed to having the traveler walk a long distance. There's also another challenge that I have a review article on this, not just this topic, but this is one of the things pointed out in the review article, is when you're simulating these systems and you have people that want to make short trips, what should you do? So 4 possible options here. O and B being the origin and destination of the traveler, the blue line being the route that the vehicle is currently on. On the first option here on the top or on the left, basically the person walks to the line, gets on the bus, and immediately gets off the bus. It's actually quite reasonable that your algorithm does this unless you tell it not to. This would be a complete waste of everyone's time to have the vehicle stop, the passenger get on, and then get back off. The second option here is to just make the traveler walk to their destination. Don't actually put them on the microtransit service, which is kind of weird because the person's saying, I want to use your service, and you're saying, no, you have to walk to your destination, our service won't help you at all. The third option is the ideal one, where your destination is in line with the vehicle's existing route. That's great. It'll pick you up, it'll drop you off with minor inconvenience for everyone involved. The fourth option here is, yeah, you are actually on the vehicle's route, but that vehicle is going to take 10, 12 minutes to get to your pickup location. And during that 10, 12 minutes, you could have actually walked to your destination already. So these are some challenges operation to deal with from a simulation perspective. And they arise in the real world as well. Deal with them differently in different contexts. All right, so don't read this slide too closely. It's just to say that, I'm talking about research challenges here. Going from ride hailing to shared ride services is a much more challenging operational problem. Going from modeling a service without walking legs to walking legs makes the problem more challenging. And doing so in a simulation environment where there's uncertainty makes the problem much, much, much more challenging. These challenges are not additive, they're more multiplicative for basically growing faster than that. All right, so let's talk about the actual underlying operational problem that we have to deal with here. What information is given to us? Well, we know the status of the vehicle fleet. We know where all of our vehicles are. We know how many vehicles there are. We know the capacity of the vehicle, etc. We have information about traveler requests. If you think about this problem from over the course of a day perspective, we don't know yet where all these travelers' origins and destinations will be, and we don't know what time of day these requests will pop up into the system. we might have some information prior to the day about what the distribution might be, the spatial temporal distribution. We're also given that we have a realistic transportation network that suffers from congestion and uncertainty. And we have a long list of parameters that will help us model the problem, which I'm going to show you later. What we're trying to find is an operational policy, really a decision model, which will tell us what decisions to make given the state of the system at a particular time. We also have to come up with smart algorithms to implement this decision policy, which we'll get into later. With the overall goal being to optimize really multiple objectives. You can think of these objectives from the fleet side and the customer side. They're not super separable, but for now it might be useful to think about it that way. Service quality being how many of the requests do we actually serve as opposed to reject because we can't get to them in a reasonable amount of time. What's the total time in the system? That is the time when you make a request so you walk to your final destination. We can break that down into walk time, wait time, and vehicle travel time. Operational cost, the metric we're going to use for that is fleet distance per request served. You could probably come up with algorithms that are heavily biased towards serving the requests that are most efficient, but our algorithm doesn't do that, so I think this is a pretty useful metric still. All right, so let's think about actually modeling this problem. In a dynamic problem, it's really important to model the current state or status of the system at any point in time. So what information do we have at any point in time, or what information would we like to have at any point in time? That'll help us make decisions in this time period. All right, so we need to know the current location of every vehicle, and we need to know the planned route for every vehicle. If we know the planned route, that means we also know what the occupancy of the vehicle is throughout that entire route, which tells us whether or not we can insert new requests into the route or not. We also need to know information about the requests. From a computer modeling perspective, it's the possibility that we don't know anything about the request yet, but in the real world, either the request has been made and not assigned to a vehicle, it's been made and assigned to a vehicle but not picked up, it's been picked up and is en route, or it's been served. So we need to know that information about every request in the system. We also need to know the current travel times at every link in our network, as well as a forecast of what the link's travel times are going to be in 5 minutes, in 10 minutes, etc. All right, what decisions have to be made? I've kind of hinted at this earlier, but this is kind of the fundamental challenge here. The first is matching vehicles to customer. It's a conventional matching problem in the base Uber and Lyft service. We also have to sequence the pickups and drop-offs for each individual vehicle. And when we're sequencing, we should also be scheduling. So that is, we're telling ourselves internally and also the customers when they're going to be picked up, when they're going to be dropped off. We're not going to use repositioning algorithms in this study, but you could easily incorporate that into the decision framework as well. And then finally, we have to choose the customer pickup locations and the customer drop-off location. Again, this is unique to corner-to-corner service as opposed to door-to-door service. All right, so objectives, again, from another perspective, minimizing the aspects of customer wait time, minimizing fleet miles, and maximizing the number of customers served. Sources of uncertainty. The main source of uncertainty in the system is we don't know when future requests are going to happen, and we don't know where they're going to happen. We might know a distribution from history or from our prediction model. We don't know exactly where these things are going to occur. There's also uncertainty about congestion in the network. And there are other sources of uncertainty, which our model doesn't incorporate, but I hope we can discuss later, which is an area of research and mine right now. Okay, so that's the problem, kind of talk about how you might model it. And let's talk now about what our operational policy is. All right, so top left here. Basically, every 30 seconds, we're going to call this module in our software. And there's going to be 4 effective stages of the decision process. The first thing is filtering out or filtering in a set of potential vehicles and requests that can be matched to each other, right? In theory, every vehicle in the system can be matched to every possible new request in the system. But we don't want to make that assumption because vehicles could be very far away from requests. Vehicles could already be at capacity. Let's not consider them in our matching algorithm. The second is to check, another type of check, as to whether or not a particular vehicle can actually meet the time window constraints associated with the traffic. So we're going to have some guarantees on our quality of service. Got to be picked up within more than 20 minutes. Your detour time is not going to be more than 15 minutes. Your detour time is not going to be greater than 50% of your base distance. These types of factors we're going to incorporate into our filtering approach. The third step and the fourth step, as is shown right here, we can do matching first and then do the selection of pickup and drop-off locations, or we can do pickup and drop-off locations first and then do matching decisions second. Okay, so if we're doing pickup and drop-off location selection first, it's more computationally intensive because we have to do it for every possible, feasible candidate request vehicle match. Whereas after we make the decision of what request should be assigned to which vehicle, we only have to do it for that particular pair of requested vehicles. So the one gives you better performance in terms of quality of matches. The other one takes longer to do. All right, so I'm going to kind of go through a number of these in more detail. Not all of them because we won't have time, but some of the kind of smart things that my team came up with to get even better and better performance in terms of operating these systems. Okay, so talking about the filtering criteria, let's look at this zone here, zone 109, which is where our current request is located. So we're looking to build a vector or a set, D sub R, which is the vehicles that could feasibly be matched with this request. So we're going to use geographic information. We're going to use this zonal system. All right, so the number of zones that are surrounding 109 are listed here. You can create a vector rank ordered by how close those zones are. And we're going to have the vehicles that are currently located in each of these zones. We're going to grab initially 10, 12, 15 of these vehicles to possibly enter into our candidate vehicle request filtering process. So this is the filtering criteria. It's actually a somewhat straightforward algorithm. Is the vehicle idle? If it is, it's in our candidate vehicle set. If it's not idle, that is, there's passengers already in the vehicle. Does that vehicle actually have an empty seat inside of it? If there's no empty seats, we can't match our request to it. Is the vehicle moving in a similar direction to our request? I'll show you more details on that on the next slide. If they're moving in similar directions, they can be matched. If they're moving in opposite directions, they cannot be matched. This U greater than or equal to 1 here is all about, does the vehicle have to move backwards given its direction of movement to pick up the request? If so, only move backwards a little bit. That could be quite inconvenient for the travelers inside the vehicle. If the vehicle, if the request would be after the last drop off, awesome, it's in the set. We don't have to worry about it. It's not going to inconvenience any of our current travelers. And if the request would be within the current vehicle location and the last drop off location, let's make sure the vehicle wouldn't have to detour too much to pick up this particular request. So this is a simple check that the angle of the Euclidean path for the traveler from its origin to destination in red is similar to the planned vehicle path of the vehicle itself. If that angle is less than some particular value, great, they can possibly be matched. This is what I was talking about before. So if the request is on the wrong side of the vehicle, we're only going to go in the reverse direction, maybe a minute or two. We're not going to do it too far in that direction. If the request is on after the last drop-off location, it's fine, it's going to be in our set. If it's between 0 and 1, that means that we have to check our detour constraints. This is the detour constraint right here, just making sure the sum of the two legs associated with the detour is not too much greater than the direct path between the vehicle's origin and its last planned drop-off location, vehicle's current location on origin. Okay, to determine the insertion position of a request into a vehicle, we use what's called an R-tree approach, which basically, there's many ways to do it, but I think we use a Euclidean-based approach. Take the vehicle's current location. What is the pickup or drop-off location that is nearest to the current vehicle's location? As long as that drop-off doesn't occur before the pickup, that particular location becomes the first in our sequence. Once we get to that location, we search from there. What is the next nearest pickup or drop-off location? We make sure the drop-off doesn't occur before the pickup. If it doesn't occur before the pickup, we insert it into our sequence. This process continues until you've inserted all pickup and drop-off locations into your sequence for a particular vehicle. All right, time window checks are relatively straightforward. We, that is the modelers, and in the real world, what we're representing is this service provider offers some guarantees in quality of service. If a vehicle cannot pick up the traveler within a reasonable amount of time, there's no possible match between these two. And similarly, if that vehicle cannot take that request to their destination within a reasonable amount of time, that request and that vehicle cannot be matched. Okay, we also need to, because we're going to be solving an optimization problem, a matching problem between the requests and vehicles that made it through this filtering process. We need to calculate what the cost of a match would be. Okay, so here's the function right here. I'm going to walk you through it. The left-hand side is for the new request, the person that has not been assigned to a vehicle yet. There's two terms. The first is the expected waiting time for assigning this vehicle to this particular request, and the detour time. So if the person took their personal vehicle directly from their origin to their destination, we know what that travel time would be. How much extra time is associated with using this microtransit service? We want to have a cost associated with both our new request waiting time and their detour time. You can easily change what the weights are on these, calibrated based on some behavioral data. I think we end up just using one for these weights here. And then we do the same exact thing for the requests that have already been assigned to that particular vehicle. If they haven't been picked up yet, that means that this new match might actually increase the time in which they're going to get picked up. It's more likely that the requests are already inside of the vehicle, and how much added detour is associated with picking up this new request. So these are all the costs that are incorporated into the cost function for particular request vehicle pair. We don't need to go into the details here, but kind of a complicated process for determining what are the potential feasible locations where travelers can walk to. Again, we want to have passengers or requests walking to locations that are moving in the same direction as the vehicles. This is particularly the case if you have one-way streets. You never want the vehicle having to reverse its direction and moving in the wrong way. We actually tested a number of different policies. So we set a walking range of, well, we're going to vary it later, 400 meters, 800 meters, 1200 meters, etc. Do you want to choose the locations that are as close to the traveler request as possible, or as a baseline, want to make the travelers walk as far as possible? Or do you just want to use a random-based approach? Maybe that'll work best in the end. The answer, of course, is it depends. In general, you do want to have your travelers walking to your main corridors, your arterial roads. In this case, we do assume that there's not many issues in terms of picking up travelers on busy corridors. Of course, don't let the vehicles pick up the travelers on the highways, but they can pick them up on the heavy arterials. All right, this is the bipartite matching function, which is kind of the standard approach for matching vehicles to request in these vehicle fleet operational problems. We actually do something that I think is quite creative. So the bipartite matching has effectively one flaw, which is that at every decision period, you can only assign one new request to a vehicle. That gives it its nice analytical properties, which will allow you to solve matching problems for hundreds of vehicles and thousands of requests, thousands of vehicles and thousands of requests. If you were to allow it a single vehicle at any time step to be matched to more than one traveler, you move into the realm of a kind of standard vehicle routing problem, and the problem becomes much more challenging computationally to solve. We kind of cheat the system. At any particular time step, we solve the matching problem once, but we have this inherent quality of service built into there, which is this p-value, which is the reward for an assignment. And if the reward is not greater than the cost, the vehicle and the request will not be matched. So if you do have a vehicle that's the only one located near a large number of requests, and there are no other vehicles nearby, in the first iteration, I'll be matched to you because you're the most closest. I will then solve the matching problem again for the remaining requests that haven't been matched yet. Because there was no other vehicle nearby, now we'll pick up you as well. So in this current time step, I'm actually adding multiple travelers to the same vehicle, which those of you who don't know optimization, maybe this sounds like it's pretty simple and stupid, but we are overcoming one of the major shortcomings of using this matching problem for shared ride services as opposed to non-shared ride services. All right, so let's get into the computational experiments. I guess I should have mentioned this already, but we use the Polaris simulation model developed at Arvine National Labs to have a realistic model of the dynamic traffic congestion in this case, Bloomington, Illinois region. We've also tested this on Chicago, but as you're going to see, we have tons and tons of computational experiments. Just a little bit easier to do it in Bloomington than it is in Chicago, given the size of the network. All right, so these are some of the parameters I mentioned earlier. Maximum time until the quality of service vehicle can't have a wait time longer than 20 minutes. 15-minute absolute detour, relative detour, half of your direct travel time. We assume we only want to have 8 candidate vehicles at most for each request. This also helps with computational performance. Number of potential pickup and drop-off locations, 5 potential pickup locations, 5 potential drop-off locations. We'll solve this optimization problem to choose which one is best. As I mentioned, we're not going to apply any extra weight for wait time versus in-vehicle travel time. I can talk about why that is at the end of this lecture if you'd like. Those of you who've taken travel behavior, that's probably, you think, a bad assumption. I'll tell you why it might not be in this case. Maximum angle associated with the direction of the vehicle and the request is 30 degrees, 300 meter or 3 kilometer remaining vehicle tour to exempt direction angle. Didn't get into that too much. Same idea for how far backwards you can go. Maximum vehicle pickup detour. We have a distance and a time base, and the maximum walk range here, which we're going to vary this parameter significantly, is 1 kilometer. Some of the parameters associated with the simulation, we're going to run it for 24 hours. We're going to take 30 seconds between each set of matching, sequencing, scheduling, and repositioning decisions. The number of requests is very large, 220,000 over the course of the day. We're going to assume that each request is just one traveler. We could and should generalize this such that our vehicles become full sooner, but for now, we're just assuming it's one traveler per request. And then for the initial locations of the vehicles, we're assuming that the density of vehicles is inversely proportional to the density of a particular TAZ. So the performance metrics we're going to use to compare these 4 different services and evaluate the quality of our algorithms are the matching rate, vehicle kilometers traveled, vehicle occupancy, customer wait time, or customer total time, which we're going to break down into the following components. All right. So we're going to do a bunch of scenario analysis. The first of those scenario analyses is going to be the walk range. What is the maximum distance we're going to allow passengers to walk? We're going to do all of these analyses by varying the fleet size. It is the critical design factor when operating microtransit services. We're also going to vary the walk speed. Why are we doing that? Well, we're going to assume how much more efficient is the service if you actually have micromobility everywhere. You know, e-scooters, you can easily fold them up and take them into your microtransit vehicle. Kind of an interesting study. And then we're going to vary implicitly the fleet's the seat capacity of each. Okay, so we have, in most of these graphs, you're going to have the 4 different service types. Green, door-to-door ride hailing. Blue, door-to-door ride pooling. Yellow, corner-to-corner ride hailing. And red, corner-to-corner ride pooling. So what do we see here? At small fleet sizes, there is a gap between ride pooling and ride hailing services. Because the capacity of the vehicles is effectively larger for ride pooling, you can serve more travelers in a ride pooling based service than a ride hailing based service. It's not a new finding. My prior work and many other studies in literature have identified this. As the fleet size gets large enough, you can easily handle these 220,000 requests that occur over the day. There's not much gap between any of the service designs. This is a particularly important service design metric or service performance metric, which is the average vehicle kilometers traveled per request served. Okay, what do we see here? At the top in green is our baseline Uber or Lyft service. So we're looking at around 7.5 vehicle kilometers traveled per request. You compare that with the low end, somewhere around 5,000 vehicle fleet size, which is our proposed service, Microtransit, corner-to-corner, shared ride service. We're getting values around 5.5. But from a percent difference, this is actually quite large. And from an absolute difference, it's quite large as well. 7.5 versus 5.5 vehicle kilometers per request. Big difference there. And in the middle, we have our blue line and our yellow line. This is also, I think, an interesting finding, which suggests that walking is nice, it's helpful, but more important is people sharing the rides with strangers. Not too surprising, but a useful finding nonetheless. Left-hand side here, we have a complementary. So I just showed you how corner-to-corner ride pooling is great in terms of vehicle kilometers traveled per request, but what's the cost? The cost is it takes a little bit longer for a traveler to get from their origin to their destination in the corner-to-corner and in the ride pooling services. Ride pooling under certain fleet sizes actually doesn't increase total travel time that much compared to ride hailing, but in almost all cases, the corner-to-corner service is going to take longer than the door-to-door service. And that's because people walk slow, right? It takes a long time to walk places, whereas vehicles are much faster. There are health benefits associated with walking. We don't really get into those too much. You can pitch it that way. And we have a discussion in the paper about how there's probably a nonlinear and non-monotonic function associated with how far people would like to walk. Don't mind walking a little bit, don't want to walk too far. There's obviously a lot of heterogeneity associated with those preferences as well. And then here we have the occupancy on the right-hand side. So our algorithm is kind of doing what you'd expect. If you have few vehicles, you're just pushing as many requests into those vehicles as possible. As the fleet size gets larger, you're going to put fewer passengers into vehicles just to have some high quality of service. But in general, there is a significant gap, of course, between ride hailing and ride pooling. Not that big of a gap between corner to corner and door to door, at least not for Bloomington, Illinois. We are seeing a bigger gap in Chicago than we are. All right, so some sensitivity analysis. The first is going to be with respect to walk distance. So my student is kind of too good at making graphs. He puts a lot of information on these things. So if you have enough time, it's quite useful. So I'll let you read this one in for a second here. We have different fleet size across the three main panels. We have door to door versus corner to corner at the second tier. And then for each of these, we're increasing the maximum walk distance. And you can see it's for the most part, a linear trend from 0 meters maximum walk distance to 1,000 meters maximum walk distance. So if you allow for or require travelers to walk longer distances, you're going to get some benefits associated with that. The benefits in particular here being VKT per request. But of course, the cost is you're going to have more time in the system if you're a traveler. You're going to walk longer. It's going to take you longer to get end to end. All right. So this is the one I particularly like, which is sensitivity analysis with respect to the walking speed. So if we actually can have people walk faster and more likely use a micromobility, shared micromobility based service, so they can maybe go, what is our assumption here, 20 kilometers per hour as opposed to 5 kilometers per hour, you can effectively take away the negative aspects of a corner-to-corner service, which is that it does take a long time to walk places. If you have people walk 4 times faster, they can get from their origin to destination nearly as quickly with that corner-to-corner service as they can, excuse me, that's the next slide, as they can with the door-to-door service. And sorry, the previous slide is just showing you do get continuous benefits in terms of reducing the vehicle kilometers traveled per request. So these values right here are not quite as low as the door-to-door service, but there's also not a huge gap between them. So quite important for us is how long does it actually take to run these full day simulations. So that matters for the types of analyses that I'm interested in as a transportation systems analyst. But what is a fleet operator interested in is how long does it take to solve individual one of these instances. So these results here kind of hide the ladder analysis a little bit. We can solve these problems in 3-4 seconds, even in the worst case. And that's not with a super high quality computer. And particularly important is that it scales quite well with the number of vehicles. Going from 5,000 vehicles to 10,000 vehicles, we only get a linear increase in the computational runtime for the system. It's not an exponential increase. And yeah, while corner to corner takes a little bit longer than door to door, it doesn't take way longer. The reason for that, kind of contrasting with what I said earlier, is that we did decompose the matching problem and the pickup and drop off location selection problem. If you tried to solve them simultaneously, you would be in big trouble. So we propose decomposing them. Solving, as I mentioned earlier, either PUDO location first and then matching, or matching first then PUDO location, which is actually what this A and B here. So this is PUDO after matching, and this is PUDO before matching. The PUDO before matching does take a little bit longer than PUDO after matching. One interesting thing with the computation runtime as well is that it does increase with the maximum walk range, as you might expect. Gives you a larger candidate set of potential locations to consider, which takes longer computationally to run. All right, so conclusion for the second study here. We developed a modeling framework, decision modeling framework, operational policies, and an algorithmic approach for corner-to-corner microtransit shared ride service. We did that at scale. We did it in a dynamic ingestible network. Didn't get into the details too much, but I think we've effectively handled the stochasticity associated with the network travel times. We analyzed 4 different mobility services. We found, as many others have, that pooled ride services do significantly decrease vehicle kilometers traveled, but also that having passengers walk to pick up and drop off locations is also beneficial in terms of DKT per request. Maybe not quite at the same order of magnitude, but certainly significant both practically and statistically. However, these walking legs do increase the total time a traveler spends in the system. I initially wanted to tell my narrative around this last point here, which is ultimately there's a 3-way trade-off. There's a user cost, there's an operator cost, and there's a computational cost trade-off. You can design systems that are quite efficient and effective for travelers, that'll be ride hailing, but would be quite expensive for a particular, well, actually, let me stay back a second here. User operator computational cost expensive. You can make design decisions within the corner-to-corner ride-hailing service, which should be quite beneficial for the travelers. You're going to need more vehicles. Those vehicles are going to travel more miles. That's going to cost the operator more money. You can design a system where people have to walk a long distance. It's going to be inconvenient for them. They're going to need fewer vehicles, and those vehicles are going to drive fewer miles. The last element of this triad here is the computational cost. If you have more powerful computers, you can spend more and more time solving these matching problems, solving these pickup and drop off location problems. You can do things that, as opposed to fully decomposing the matching problem in the PUDO location selection problem, you can have information passing between them. But that is going to cost you computationally, which is not only a problem, but if you don't actually make decisions in a few seconds in the real world, well, people don't get picked up enough. A bit about future research. We do want to spend a little bit more effort in making sure that vehicles that are occupied aren't waiting for travelers to pick up and drop off locations. To do that, we're going to try to not always call the router for every potential vehicle and request match, but we do want to strategically call a router such that when the vehicles and requests are close to each other, that the Euclidean distance approximation of the actual network travel time is not a terrible approximation. That's something we're working on right now. If the vehicle and request are far apart, the Euclidean approximation, which is the straight line distance, is not a particularly bad assumption. If the vehicle and request are close to each other, the approximation is quite bad. We spent a lot of effort intellectually and computationally to make pickup and drop off location decisions online or dynamically within the day. There's actually now some other research that suggests that you don't need to spend that much effort making these pickup and drop off locations. If you know where the request origin is and you generally know which direction it's going, you can have a predefined subset of pickup locations that are quite convenient. And you might as well just choose those beforehand when the person makes the request, which has the added benefit of the person themselves doesn't have to deal with the uncertainty of figuring out where to get picked up at, right? They kind of know where they're going to have to go depending on where the destination is. And then kind of what I'll talk about in the next slide, last point here, is where do these services make the most sense, particularly the public sector microtransit-based services. All right, so let's talk about that for just one slide, but a number of seconds here. So these are all the service design parameters that I think are particularly important when thinking about designing microtransit. Fleet size is huge. It has an enormous impact on all the metrics that matter, cost and service quality. You have more vehicles, it costs a lot more, but you're going to have much less wait time. You're going to have much more reliability. You're going to be able to serve your requests more frequently. Vehicle attributes. What is the right size for the vehicles? Is 4 seats enough, or do you actually need 8 seats? The answers to these questions are always context dependent, but you need to think about them up front. What fuel type makes sense? What are the goals of your microtransit service? Are you developing this microtransit service to actually reduce greenhouse gas emissions? You should probably make a different fuel type decision than if you're just trying to reduce cost and maximize service quality. What should the size, shape, configuration of your service area be? We talked about this earlier. I promise this is actually already on my slide, but do you want to have subzones? 5 different zones that make sure the trips are all within those zones, maybe feeding people to the fixed route transit service? Or do you want to have one big region, right? I'm an optimization person. Doesn't make a lot of sense to me to break up the zone, just adding constraints that you don't need to have. But of course, in the real world, I'm missing a few things, which is that when you have a larger zone, people, for a number of very good reasons, are going to want to make longer trips. If people are making longer trips to potentially inconvenient locations for the service, that's going to cost more. You also have the benefit of providing people the mobility they want, but it's going to cost more. Pickup and drop off locations, I've kind of went into this a bit already, but are they ubiquitous? Can you get picked up and dropped off anywhere? If that's not the case, how densely populated should the pickup and drop off locations be? This is actually quite important for automated driverless vehicle-based services. So we had Pony AI or Hyland at the time operating in Irvine, and they only allowed for pickup and drop-offs in basically 20 spots in the entire greater Irvine area because they wanted to be sure that their vehicles were safe, people were safe getting in and out of the vehicles at these locations. 20 is not very many pickup and drop-off locations, though. So either people are walking a long distance or they can't get to actually many destinations. So it's probably not 20, maybe it's not 2,000. What is the right number and what are the right locations that these allowable pickup and drop off locations? If you have fewer, your service can operate more efficiently than if you have efficient from a cost perspective. Depot locations, something to consider. Where do your vehicles start the day? Where do they end the day? Where do they have to go if they're empty during a particular period of day? Hours of operation is a particularly important service design consideration, again, given your context, right? Is it a college campus or is it a city with very few young people? Does your fixed route transit service stop at 6 o'clock? Do people feel comfortable on the fixed route service after a particular time of day? Would they feel comfortable on the microtransit service? So hours of operation is particularly important service design consideration, particularly when it comes to the costs associated with the drivers. I'm not an expert at all on driver costs and labor laws, etc. But I know that if you have drivers operating more than 8 hours, it becomes more expensive. If you have an entire service operation that is some uneven number, it becomes more costly than just one additional vehicle hour of service. Fare structure, this is particularly important as well. Should it just be $2 for every ride? If you're providing first and last mile service to public transit, should the fixed route transit be free after you use the microtransit service? If it's the same cost as the fixed route service, why would anyone ever switch to the fixed route service? So these are all important questions. Should you get a discount for going first mile, last mile? Should you allow requests to be scheduled? Should you require requests to be scheduled, or can you handle immediate on-demand requests? And then what are your implicit or explicit service quality constraints? So what are you designing for your average, your 95th percentile wait times? And what is your limit for, if we know we can't serve this passenger within X minutes, we're just going to tell them we can't serve them. These are important considerations as well. Same idea for detour distance, detour time, as well as walk distance. This is kind of the same information in a fancy diagram here, but inputs, modeling parameters, and the outputs versions. I will leave it there.
Thank you for your presentation. But I was particularly, I wasn't sure if I missed it or something. Questions about the quality that you're considering, if it's a time-based quality, like reliability, or if it was occupation. That was one question. And the other question I had is usually ride-hailing services or providers are not spread out evenly in the space, so they do take longer time in some areas than others. And I don't know if that is incorporated in your assumptions and if you're considering that.
So the first question, when I was saying quality of service, I just meant the transportation attributes, wait time, walk distance, and in-vehicle travel time. So when I was saying quality, that's what I meant. Second question, amazing question. So we are not developing a descriptive model of what exists now. We're prescribing the way we think the system should operate. I actually haven't looked into the spatial equity aspects of our particular design. I would imagine there are some discrepancies in wait times depending on the subregion in the Bloomington network. Bloomington's kind of homogeneous and relatively small, so the issues might not be huge there. But in Chicago, in fact, I know in Chicago, the service quality is much higher in the dense areas than it is in the areas that are not dense. We should look into that to see, one, what is it and how can we correct for it if we think that's a particularly important thing. I was actually on a call with VIA the other day, and they were saying they have a scheduled-based service and a non-scheduled-based service, right? So on demand or scheduled. And the way it tends to happen is if you live in a less convenient area for the service to operate, you're more likely to want to schedule a ride, which means the scheduled rides are much more inconvenient for the service in the end than the on-demand rides. And this person was arguing that, well, you should probably charge more for the scheduled service, not because in general scheduled is more challenging, but because as the result of the system, the inconvenient rides are the scheduled ones. You probably want to get into it. This brings up a whole range of accessibility and equity issues. Why are people either forced to live in these areas that are low density and inconvenient, or why are they choosing to live in these areas that are inconvenient and low density, right? I know Chicago pretty well. There are people that are living in low density, currently inconvenient areas because they have to. And there are people that are living in other low density, inconvenient areas because they choose to, because they want a big house and a big garden, right? So one rule of thumb is probably not going to work, but if you are intentional about how you design these systems, how you price them, you can probably address some of the equity issues.
Thank you so much for the presentation. I've got a couple technical questions. Start with the easy one. Do you assume that each traveler is just one person, or do you account for multiple travelers at one?
In this one, we did one request as one traveler, but other work, we have a distribution, 1 to 3.
How does that change the outputs?
So in Bloomington, it doesn't change it very much because average vehicle occupancy was not particularly large, right? So And even like maximum vehicle occupancy, well, maximum is the wrong word, but very rarely are a large number of the vehicles fully occupied. In Chicago, it's an issue if you assume your capacity is full for bus.
Sure. And then second question is, can you talk a little bit more about how you do your non-Euclidean or your Euclidean distance in like a road network? Because it's not an open, clear plane.
Well, we assume the road network's not there.
There you go. That solved the problem.
Yeah, because we know the geolocations of the pickups and dropouts. So we just what's the distance there? I think we multiply it by like a 1.6 or something like that to get a better estimate of the travel time. But we still do rely on a lot of Euclidean distance stuff.
Gotcha. Thank you.
But can I add something to this as well? I mentioned earlier, it's a computational issue to solve these shortest path problems. It is for us as researchers, because I don't have 5 million parallel processors. But if you put the computers in the vehicles, they can compute their own shortest paths, send that information to a central server who then has that information to use.
And that information can be pre-calculated. You don't have to do it
Right.
online. So, if you just prepare it offline, we did this for some other research projects. It takes a couple of hours to sweep all this, get all this done. And then when you do the online calculation, it's just retrieving information. It doesn't take much time.
So agreed. We have a skim matrix that we use for Chicago, which works pretty well. But in Chicago, we can't store an all node to all node shortest path calculation, right? The memory just goes to the roof.
Right.
There's probably, I'm sure you've done, I'm sure there are smart ways to deal with that.
Right. You have to find a certain discretization level, and then you add extra door distance to that where the center of the zone.
Okay, yeah, exactly. One thing we have found though is like, you have to use detailed networks to get these things right. But one thing I'm working on now is like, I really want to calibrate my models to actual microtransit systems that are operating now. That's like a very practical thing, but I don't think it's a very important research thing right now. There's too many of these studies, including my own, that are over-promising, suggesting the quality of service and costs are just lower than they actually are in the real world. So I think calibration to actual microtransit systems is critical. Once you calibrate, then you can change things to improve upon the existing services, but just doing stuff like this where it's not well calibrated to the actual stochasticity in the system, run into trouble. Sorry, you got a question.
Yes. So regarding the pooling models that are being implemented and utilized right now by the host of ride hailing companies, I mean, how do their models differ from your model?
I don't know exactly what they do because they won't share.
Just right here.
Yeah, I know. I know when I started this work, they weren't doing this batching where you would wait 20 seconds, wait 5 seconds, and match the vehicle's request. In the beginning, Uber was just giving each driver the nearest 3 requests, and the driver would grab the request that was convenient, which my dissertation work showed was like extremely inefficient. The batching, which I know they do now, it definitely improves. What exact algorithms they use, I'm not sure. There's some work, kind of like the standard, in my opinion, best one is like Alonso Mora, 2017 at MIT developed. So he used this thing called a shareability network. They actually allow for multiple travelers to be assigned to a vehicle request at any one period of time. They mostly get around the computational issues with that. If you have thousands of vehicles and thousands of requests, you do run into bottlenecks. But that's, I think, probably the state of the art. You know, I can send you a paper.
I was wondering, in your bipartite matching formulation, you use like this cost minimization function?
Yeah.
Is there a reason why you're using cost minimization as opposed to profit maximization? Because like first one would be like a condition of profit maximization. And
I guess that the second one makes more sense if we're trying to do this for private companies like via.
Yeah, so it's a great question. Sorry, did I cut you off?
No.
Okay.
I have a second question, but I'll let you answer.
Okay. Important to understand that it's an objective function only, it's really a control function. It controls the vehicles within the simulation. Naturally, there's some connection between that objective function and your overall objective function, which in my case is minimizing VKT request, but it's not a one-to-one relationship. That's ultimately just a control function, right? So a private company or a public company could use this same function the same. To answer your first question, I don't know. I chose minimization because I initially started from minimizing cost, requiring that either all vehicles match the request or all requests to match the vehicles. And then I didn't want to have that stringent constraint anymore, so I just subtracted a profits. But I teach optimization, so max of z equals min of negative z,
Yeah.
which is what you can do.
Yeah, I guess can I just follow ask, because you actually don't have price as your variable. So if he had a price as a variable based on supply demand relation, then it won't be equivalent. But because the price is actually fixed, right? And then so it doesn't matter.
I see.
Yeah, the way I've always tried to explain it is like, people make these requests, there's certainly some filtering process where they get their price, whether it's public or private. And then the request comes to me as a central operator. My job is to serve the request that made it past this filter as best as possible. Right? And I have that minus P, which is just my way of saying, if that request is too far away, I don't want to serve it right now.
I have a second question, but
Yeah.
go ahead.
I think you haven't got one. I've been biased towards the front. Inequities here. Go ahead. Yeah.
I have two questions. First one, can we go back to the slides with the filter criteria, please? Thank you.
If you have more, please
The
let me know.
filtering criteria is.
Oh, sorry.
Yeah.
Going with the flow chart at the bottom?
Yes. And their vehicle canvas there. So I'm curious, in this framework, we only consider the vehicles that already have passengers, right? Then if the vehicle is empty, then it becomes candidates automatically. Is that the second command telling us?
Yes and no.
I know, there,
This one right here, right?
yes.
So the answer to your question is yes and no. So at this step in the algorithm, if it's idle, it's in. But if you go back to the prior slide, we had to make sure that it was within this larger candidate set. It can't be
Yes.
too far away.
Yes, so then my question is, in the analysis, as the number of vehicle increase, does the framework tells us what proportion of vehicle actually empty for at a certain time stamp? So I know, like, as the number of vehicle increase, there's only a certain amount of population there. Then if the vehicle become more, then there would be a proportion of vehicle running without passengers at a certain time.
I'll try to answer what I think your question is, but you can ask again. So we allow for a fixed number of idle vehicles independent of spatial location of the request or the relative number of requested vehicles. It's possible that there are currently 0 idle vehicles in our simulation, in which case we can't add them to our candidate sets. That didn't answer your question, maybe you can ask again.
Yes, but just refer to the graphs at the end of the funding, which the matching rate increase as the number of vehicle increase. Then,
Yeah.
but also means there's a proportion of vehicle probably don't have passengers.
Oh, in the results,
Yes.
towards the right end.
Yeah.
Yeah, certainly as you have more vehicles, the average utilization of the vehicles is decreasing.
Do
For
we
sure.
know that roughly number or proportion of that? Like, because that also impact their efficiency at the system level, also operation and travelers.
Yeah, I think my results, I hope implicitly show that you don't need
Yeah,
all the vehicles on the right end of that graph.
Really, sorry.
Yeah, so I would hope that a decision maker would use this graph to maybe identify that like you're in the range of 4,000 to 6,000, like where you want to be. Not
Okay, now it's
10,000.
there. Okay. So my second question is, you talk about ride hailing and micromobility, like e-bikes or bike sharing, like basically there's a connection between the sharing mobility together. But like, have you considered in the research that because for locality, those two are very different, ride hailing and e-bikes or bike sharing systems, because one requires the infrastructure like just driving the multiple lanes arterial, the other requires the perhaps new infrastructure. And I think that's a really big challenge for them to consider. If we don't have infrastructure, there's no way to jump into the service.
I agree. I agree. Yeah, no, certainly. We didn't look at infrastructure at all. We assumed this. Yeah, in Irvine, you can ride these things on sidewalks, but that's probably not the case in many other places. Yeah. Well, let me let you behind the scenes a little bit. We assumed faster walking speeds during our testing scenarios because weird things were happening and we were getting worse performance for the corner to corner than we were door to door. We're like, something weird is going on here. Let's just make the walking speeds really fast. And if the walking speeds are really fast and we get better performance metrics, that means we need to do a better job of picking up and drop locations. So that was the case. We fixed some things and we're like, hey, what does this actually mean? What does the 20 kilometers per hour actually imply? You know, is that just fast people? We were like, well, you know, people are going to be owning e-scooters in the future. Maybe they could use them to get to and from pick up and drop off locations.
On the other hand, we talk about the 20 miles per hour for driving.
Kilometers per hour, sorry.
Oh yeah, but like if you transfer that to miles, it's still very fast speed.
It's like
Yeah.
12, I guess, exclusive of 12, but you can walk it, so that's running.
I'm still on the high.
Yeah, you very much. Yeah.
Oh, Mike, I have a very specific question. You have, I'm trying to understand, seems like you had some filtering that is based on simulation. How does that filtering build in the analytical model? Is it just contributing to the definition of the feasible set for your choice? I didn't see the connection.
I think there's not.
So it's two
It's just-
separate steps. Because it's hard for me to imagine how the filtering help or be
By
part
the
of
analytical model, are you referring
the
to?
by, yeah, you had some minimizing. Right, so I was trying to understand where the filtering go. Is that maybe the set of
Just here, VR.
okay, so it's that the choice, the set is actually based on the filtered
Exactly.
locations.
So
Okay.
all that effort was to make sure that, you know, my original work was like 1,000 by 1,000. Instead, we're doing 1,000 by 8.
Yeah, I feel your pain. It's, you know, even it's multiple vehicle routing problems are notoriously, you know, difficult. Did you talk to people who might be using microtransit? Do they prefer dynamic virtual location or fixed virtual location? I'm just imagining myself. I don't want to keep changing
Oh,
location.
you mean like human users, not
Human,
like us.
yeah, no.
That was the
human
wrong example.
users.
I thought you meant like people that own and operate microtransit.
No, I mean end users.
Well, yeah.
Having like an offline, fixed virtual locations would make your problem much easier.
Yeah, so the one study I'm aware of was actually, you might be aware of a case at MIT, Sebastian Martin, he's at Northwestern now. They actually implemented the test in Lyft, right? I think this was for corner to corner ride hailing. They didn't have ride pooling, but they found that having this offline pseudo selection only decreased operational efficiency slightly, but it increased customer retention to a much greater degree, such that it increased their profits as their analysis because of the simplicity.
Right, Carrie, your previous project also had a fixed virtual location, right?
Yeah, we had fixed locations, but they were so frequent that, I mean, it could have been considered door to door practically,
Right.
right? Like there
Okay.
were so many of them.
Very, very dense.
Yeah, very, very dense. So,
Pascal said he fought for that though, right? He
Yeah.
fought,
Yeah.
yeah.
but the reason we did it in that case was that Marta wanted to check literally every one of these destinations so they could pull out any of the locations that they felt were dangerous to be picking up and dropping off a person. And so that's why we actually had points, is so that they could then remove a few of these points from this almost infinite number.
Yeah, I think I asked him that, like, can you do a good job? It's like, yeah, as many as we could get, we got. If you don't have, go ahead.
So I had, oh yeah, thank you. Your presentation. You mentioned trade-offs. This may inform, like it's based on your results, it makes sense to have a fleet of about 5,000 cars. This is for Bloomington.
Yeah,
So what's the population? Like this could really inform decision makers. At what point it's best to have a fixed route, especially if it's AVs, versus a massive fleet, because the cost of automated vehicles that fit, that fit 4 people, and you have 5,000 of those cars with a very complex computational problem, versus having maybe, synchronized with existing transit, I don't know if you looked into that.
so I mean, again, let you under the hood, we wanted to have a big number so we could show we could handle a big number. So that demand level is not in any way supposed to match what we do. Okay, having said that, I love your question. I'm trying to get at it in other research, which is where can microtransit replace fixed route transit? Where does it make more sense to operate microtransit? As I've told a number of you, Sandag is interested in where can we run these services side by side, where the microtransit mainly acts as a feeder service to fixed route transit, but also can get people to destinations that are not served well by microtransit. That's going to be costly, but their point is like, we want to have a multimodal transportation system. We don't want to just talk about it, we want to actually have a multimodal transportation system. And that involves fixed route and microtransit side by side.
I have another question about the modeling or two related, maybe. So one was, you mentioned that it was a daily model, and I did want to understand if it's like, again, you're assigning equally number of vehicles for the whole city continuously, or you're assuming like daily pattern that is like peak hour, low
Yes.
peak hour, and also like concentrations of vehicles in certain areas because of that daily movement.
Yeah, so the spatial temporal pattern is consistent with Bloomington's real world spatial temporal pattern. So we have the peaks in the middle of the day, we have the correct directionality of where people are going to and where they're going from. I should have, I haven't tracked exactly where the vehicles are throughout the day. That's something that we should do. Irvine has, well, I think they have a visualization tool we can use to see where the vehicles are throughout the day.
And you keep the same number across the day because
Same number of vehicles?
because in lower hours you don't, like in lower, like valley hours you don't really.
Yeah, no, good point. We assume the vehicles are just always there.
Then my other question, I guess, builds on what was asking. Like, you were optimizing BKT for lower BKT. What happens if you change that to lower average travel time? And do you get like something different in the number of vehicles or like the way you optimize the system?
Yeah, okay. So this is an optimization problem, right?
Yeah.
And you're looking at the objective and it's to minimize costs.
In kilometers.
In kilometers, yeah. But this is not actually the model of the full system, right? This is just the decision model we use to make decisions throughout the course of the day, right? So I often call this the control function. Because it controls where the vehicles go throughout the day. I actually don't have an explicit objective function for what I would call the sequential decision problem. Sequential decision problem meaning the idea that you're making a lot of decisions across the day, and you want to make the best combination of decisions to meet whatever your objective is. So when you use policies like reinforcement learning, you need that objective function such that you can learn through a lot of simulation what the best policy is that's going to make those decisions out there. I said, well, I kind of know, I know reinforcement learning doesn't work here because the decision space is way too big for it to handle. This is kind of just an optimization-based control policy to move the fleet. I can tweak the parameters to push things more towards shorter travel times and less worse VKT per request, but I don't have full control over it in the way that you're suggesting. It took me 4 years to be able to even come close to being able to explain the distinction between this function and a conventional optimization problem.
So I think with that, it's after 3 o'clock, and so we're gonna cut things off, but thank